Welcome to the discussion on the topic horizontal shear stresses in beams of rectangular and triangular cross sections. By the end of this particular discussion, I am hoping that we'll be able to learn how to sketch the shear stress variation in rectangular cross sections or even triangular cross sections, right? We will be able to, I'm sure that by the end of this discussion we'll be able to do this particular tasks, right? We'll be able to sketch the variation in the rectangular cross section, beams are having a rectangular cross section as well as triangular cross sections, right? So let us start that now. For doing calculations of shear stress in any of these cross sections, there was a governing differential equation. We should always keep in mind how that derivation has been taken place, right? That we have discussed in the previous session with all the details, how the shear stress, horizontal shear stress development happens in case of beams subjected to um, transverse loads, right? So this is the governing differential equation. If you want to find the horizontal shear stress, right, at any cross section, at any anywhere in the cross section, you can find it anywhere at any depth, at any layer or plane. If you want to find out, you can find out. The expression was tried to be given here. Tau xy is the shear stress at a particular plane, right, at a distance y from the x plane, right? Tau xy is equal to v times x, v suffix x, in the sense what we are saying is at this particular no at this particular cross section the shear force developed, the maximum shear force developed, that was taken as vx, and I is the moment of inertia and t is the width of the section or plane that we have considered, right? And then your y, of course I already discussed, it is the distance of the plane that we have taken, right? So that plane, so this y is nothing but it is the distance of the plane that we have uh, considered, right? So now your expression for finding the horizontal shear stress at any distance y from the neutral axis is nothing but vq by it, where q is no first moment of area of the given plane, that planar area that we have taken, right? Y ty dy, where ty is nothing but the width and y is the distance of that particular plane which is considered, which is at a distance y from the neutral axis. The same this particular term can be written as area times the centroidal distance of the same area from the neutral axis, right? A y bar. In other words, this term is the key term because the rest of the things we can see here, the rest of the things here, uh, they are mostly constants that we can determine at a time. So what are changing? The term that was changing here is qy. So if you are, this is the key one, and if you could find out that straight away you are having the shear stress is at our fingertips, right? So this a dash y bar or a y bar you can call, right? What is that term? If you understand, that's clear of the entire equation. So this is the top or bottom. One can take this plane either above the neutral axis or even below the neutral axis. Doesn't make any difference. So it is the top or bottom portion of the member's cross sectional area defined from the section where dy is measured. Okay. So we have taken at a distance y. At that distance y, Of course, the thickness or width is width, we are saying width of that particular plane is ty, right, at that location. Now this above area only you have to consider. Okay, and y is the y bar is nothing but centroid of this particular area whichever we have chosen from the neutral axis, that becomes your y bar. So with this particular term is the key term, we can easily establish the shear stress equation at any desired location along the depth. Okay, let us start with this basic understanding. So we are going to use from now onwards throughout all our discussion the same equation is coming back again and again. So let's see the how you can determine or plot the horizontal shear stress in a rectangular cross section, right? So how we can do that? Let's see that. Here we have a rectangular cross section having a width of b and a height of h, right? Now our task is to find the horizontal shear variation tau xy. So the formula for that is we just now discussed vq by it, where q is nothing but ay bar or even yda, right? Either you can take your expression is tau xy is nothing but vq by it, okay, where q is first moment of area and I is the moment of inertia, and t or even if you can take is it b or any symbol you can use. This is basically the width of the section and or the plane that which you are considered, right? And v is the shear force. This q is what rest of the things known to us for a rectangular section we know will be given what is the shear force, depending upon the loading on the beam and on the position of the loading, and even the magnitude was given, the location was given, and the span details are given, we can easily find out the shear force. So it is a kind of one a known value for us, and the width of the thickness also you can find out wherever we desire to find, and moment of inertia depends upon the type of cross section. Is rectangular we have some value, triangle or circular. Okay, so this is what we decide to find at this instant. So is we can say either ay bar provided the this ay bar you can use when the no the plane that we have taken having a symmetric cross section, but sometimes it may not happen at those times. We can use instead of ay bar we can use integral yda, both are same. In other words, we are because the cross section is continuously changing in those places, what we can do is we can take a small strip, a rectangular strip, and you can integrate it over that particular area. So either way you can use this q, right? Because here the section that our plane that we have taken is having a symmetric shape, as that of a the plane that we are considering is similar to that of entire cross section. So we can use straight away ay bar. We can calculate the first moment of an error straight away. So for that what we are doing is, let us find out this ay bar first. So we have taken the rectangular cross section having same one b here and h here, and we have taken a plane at a location, we have considered small planar area here, right? Here this particular area we have taken at a distance y from the neutral, this is the neutral axis, from the neutral axis at a distance y we have taken this particular plane area. Okay, this is y, right, and this whole height is h, whole height is h, from neutral axis becomes h by 2, the remaining distance will be h2 minus y. So in that particular case, what will be the area of this particular one? This is a kind of a rectangular area which we can write it as b times height. Width is b, right? At this particular distance y, this is the width, same as the width of the rectangular section. So b times this height of the area. What is the area? Area was not there fully. It was there only up to this the shaded part, right? Because we have taken a line here. This is the plane we have taken up to that plane, above that or below that. You can take this plane either above or below. So once that was understood, now we can put that b times h by 2 minus y is the area of the shaded part, right? Then into what you are having, and then left with y bar. So that means I need the centroid of this particular location. This is the location of this, but this area centroid, right? So where it will be at the half of this particular distance, either from this way or from this way. From here to here it will be h by 2 minus y by 2, or from the top h by 2 minus y by divided h by 2 minus y whole divided by 2. Now I do not want the y bar from either here or here or from top. I want from the neutral axis. So what should I do? I need to calculate this distance, say this one. So what should I can write for this? This particular distance is nothing but half of this distance, right? That means from here to here, right? From here to here, what is the distance? From this particular point to this particular point. What is that? H by 2 minus y by 2. Y whole divided by 2. I want from here, from the neutral axis. So you add that with y. So y plus, this is y. I need this whole distance. For that, what I am doing, here to here and here to here. To get here to here, what should I do? Total distance from here to here is h by 2 minus y. Center of that will be half of this particular distance, that is h by 2 minus y by 2. That's it. That's we got y bar, right? So once you got that, it's no almost over. You can just straight away put the rest of the values which we know. So we got that. So once you got that, of course we can make, simplify this. This is b times h by 2 minus y. This particular one, what can I do is, this is y and this is minus y by 2. So 1 minus half becomes half. So this becomes y by 2, right, plus h by 2 means h by 4. So I can write this term as h by y by 2, or you can say y by 2, because y minus y by 2 becomes y by 2, plus h by 2 becomes h by 4. So you can take common 2 from this. You will be getting, if I take 2 common from the denominator, you will get h by 2 plus y, right? So h by 2 plus y is here, h by 2 minus y is here. So you will be getting h by 2, right, a plus b into a minus b, something like a square minus b square. So h square by 4 minus y square divided by 2, because 2 is there. That's it. So we got 1 by 2 taken outside, a square minus b square, h square by 4 minus y square times b, right? So you just put this value in the fundamental governing equation, that is vq by it. So q is nothing but ay bar, which is just now found out, half times h square by 4 minus y square into b divided by bh cube by 12. So there you got the equation as 6v by bh cube, right? So this is now simplification of that. So 2 goes 6 times, so 6 goes to the top, then 6v, right? Then bh cube is anyway is available here, so you can take this this side. So what was the left with? H square by 4, right? What else we are having here? H square by 4, what we got here is, yeah, half into h square by 4 minus y square, right, into b divided by bh cube by 10. 1b will be available here, right, because the width of the section is also b. So that b and this b get cancelled. Then we got here 6v by bh cube times h square by 4 minus y square. Look at this equation. This equation is a of order second order, basically representing a parabolic variation, right? So the shear stress distribution across the cross section is varying in the parabolic fashion. It is a varying in the parabolic fashion, right? So the shear force intensity, now if you know how it is, if you want to draw the different locations along the depth, you can keep varying the values of y, because it's a function of y, which is nothing but where you take the plane. So you keep changing the value of y. So if you put 0, y equal to 0 means exactly at the neutral axis. If it is h by 2, that means at the extreme fibers. We know at the extreme fibers it is 0. So h by 2 if you put it, you can see h by 2 if you put it, it becomes h square by 4. You can see that means our calculations are on the right way, right? So it get cancelled, you will be getting 0. 0 at the top end, at the bottom end. And if you want to get the maximum, right, obviously this term should be 0. So that means at the neutral axis. So if you put 0 here, you will be getting 6v by bh cube times h squared by 4. So it becomes 3v by 3 by 2 becomes your 1.5 times v by a. But what is v by a? V by a is the average shear stress. Average shear stress formula for a rectangular section is, how do you get the average shear stress? Is nothing but shear force by area of the cross section. Shear force is V, cross sectional area is BH. That's all. This is your average shear stress. Now what you got here? This is 3 by 2 times VA. Simply V by A or V by BH is your average shear stress. Now what you got is 3 by 2. That means your maximum shear stress is 1.5 times the average shear stress in a rectangular cross section. So that's the target, one of the our target, that we could able to now draw the shear stress distribution in the rectangular cross section. So what you do is you put a 0 value here, that means at the ends, right, and you put a value here, 1 point, your tau max value, that is 1.5 times, right, what you got here, 3 by 2, right, because this y is cancelled out, 0. So you will be getting 6v by h goes one side, 6, so 3 1.5 v by bh, you got that value right as a tau max. Okay, now join with the help of a parabola everything, all three, you have three coordinates, right, join it, right, that's it. Then you got the shear stress variation, right? So this is how you get the shear stress variation for a rectangular cross section, right? So we have accomplished one of the task out of the two. So now let's move on to the, with the same understanding, we can move on to the triangular cross section. So we take a triangle here, the triangle having a base of B and height of H, right? Now I need to take a plane, say E of plane I am taking, which is at a distance y from the neutral axis, right? So I am going to use this area, let's shade that area, so that above EF whatever is there, that's what you have to do. Always you take a section either at some distance from the neutral axis, and above that area or even below that area you must shade that, because that's the area that we are using for the calculation of first moment of area, namely Q or AY bar. Okay, so this is the shaded area, right? Now what we are supposed to calculate, for this particular area only we need to calculate our AY bar. For this only we need to calculate AY bar value. Okay, so let's do how we can do that, right? That AY bar, how we can do, right? Let's see. So we have considered a plane EF and we have taken the shaded area. Now let's move on. Our task is to find AY bar, because rest of the things, for a what you call triangular section, we know the value of the moment of inertia as well as area also, right? So if you could find out the AY bar, our task is done. So how to find the AY bar for this area, only for this area. So for this area, temporarily we don't have any width, we do not know, so let us assume some value, is this just is b, let's see, assume b dash or b prime, and take another height, the height of that particular triangle. This is a triangular area. So this triangular area, the height of that particular triangle is say h dash, just as this is h, this can be h dash, right? So we should be finally able to express that b and h in terms of the original section, right? So what we do is that first thing our task is to find the area, then y bar of that, right? Okay, then you take the, first of all, you write this b dash and h dash in terms of b and h, because ultimately we are going to find out the things in terms of the original cross sectional details, right? So convert your b dash and h dash into b and h. How to do that? Because this is a similar triangle, aef and abc, these are the similar triangles. So using the similar triangles principle, your this b dash by b or b by b dash in either way equal to h by h dash. From this relation you can get your b dash as b h dash by h, right? Similarly, I can get the h dash value in terms of your h. How can we do that? We know that for a triangular section, the centroid from the top or apex will be at a distance of 2h by 3. From the base it is at a distance of h by 3. Okay, I need to find out h dash. Now I have already taken a plane at a distance y, so I know this value total, and I know this depth. I can get this one, which is nothing but h dash equal to the total depth up to here minus this one, 2h by 3 minus y. So you got your h dash. See, since you got h dash in terms of h, put that in the no b dash value, so that you will be getting your b dash in terms of b and h. So that was transferred. So now we are ready to calculate a y bar, right? Because we are able to transform b dash and h dash into the original dimensions of the cross section of a triangle, right? So now you get a y bar straight away. How to get that? Let's see. Your it says triangle area half b dash h dash, half times b dash is simply put this value, h dash you put this value, right? So b dash and h dash you got it. Now the centroid of this particular triangle, small triangle, you take, right, from the neutral axis. So just as this is 2h by 3 and h by 3, similarly this becomes 2h dash by 3 and h dash by 3, right? So that we want from here, that means y plus h dash by 3 from bottom, right? This is the centroid, so centroid of this will be at a distance of h dash by 3. This becomes your h dash by 3, right? So I require, so I got h dash by 3 value. Now this is your h dash by 3. Now I want distance from centroid from here, neutral axis, so add that y value. So you got it. Simplification of that, right? H dash is already we found, this is our h dash, 2 h by 3 minus y. Simplification results in 2 by 3 times y plus h by 3. So you are now equipped with all a and y bar also. So simplify that, you will be transforming your equation into b by 3 h times 2 h by 3 to comes here twice, right? So square of that particular term into y plus h by 3. So now you are ready, you put your y onto your basic equation. So your tau is equal to vq by it, right? So substitute the rest of the values that we are having here. So the values are v, and ay bar is the basic term that which we have calculated. So substitute that, right? You have I value here. As of now you can keep that I as it is, right? Try to no here we are having a tau equation, we do not know where the maximum occurs, right? Because the section is not uniform, right? So we cannot say it is at the neutral axis or somewhere it occurs, we do not know. So we have to calculate that. So write the t in terms of h and y, and then we can find out where it is maximum. So you got this particular equation. So here ay bar you have substituted just now what we have calculated, that one, this is the term v by 3h times 2h by 3 minus y square times y plus h by 3, and your t thickness, width of the section is nothing but your b dash. So b dash is, this is the value, right? So b by h times 2/3 of h minus y. So put that value here. Simplification leads to this way, right? Here 2h by 3 times y here, and minus y, what is that, minus h by 3 times y. So this becomes 1 hy by 2 hy by 3 minus 1 minus hy by 3 becomes hy by 3. Rest of the terms are okay, minus y square, and then 4h is 2h square by 9. Put it. Now we have a function tau in terms of your y, right? This is the equation in y. I need to know the value of this function to be maximized, right? So we know from the simple mathematics, whenever you want a maxima or minima, we can make the differentiation of that function equal to 0. So with respect to y, if you differentiate it, make it to 0, right? So whatever the rest of the terms are anyway constant, this is a constant term, so this is the only term in terms of y. So h by 3 it becomes when you differentiate, and this means 2y. Rest of the things other go to other side, become 0, and your y equal to h by 6. This is, that means we are going to get the maximum shear stress at a distance of h by 6 from the neutral axis. But if I want from the base of the triangle, you add the centroidal distance, that is h by 3 plus h by 6, that becomes h by 2. In other words, from the base the maximum value occurs at a distance of h by 2, right? So the maximum shear stress is at a distance of h by 2 through the base of the triangle, or h by 6 from the neutral or centroidal axis, right? So you substitute that, because our measurements are taken from neutral axis. Whenever you want to get the maximum value, you have to put h by 6, not h by 2, right? So put that, you will be getting 3v by vh finally. Okay, so maximum shear stress will occur at a distance of h by 6 from the neutral axis, right? And at the from the what you call, from the at the neutral axis, if you want, what you have to do, put y equal to 0 in that equation, right? If this no, this is the equation you are going to get. So once after simplification, this is the equation, you put y equal to 0 there, you will be getting the value at the neutral axis. So this is the value at the neutral axis, right? So this is the neutral axis value, 8 by 3 times v by h and 3v by vh. So among this is the maximum value we are saying, right? So we can plot this. So we know at the ends it is 0 all the time, either at the top or bottom, and we know the maximum value occurs at a distance h by 2 from the base, if you want to, right? So if this is the base, h by 2, so put the maximum value, join them with a parabola, that's it, we got it. If somebody is interested at the neutral axis, they can also plot that. No, here it was, slightly the position was slightly displaced, but it comes somewhere here, right? H by 2 means, and then exactly at the neutral axis this value comes 8 by 3 times v by h. Okay, so that's all. So we could, now we can check whether did you able to plot it, the shear stress distribution in the rectangle and triangle section. That's it. Thank you.